next thing we'll think about is what is the electric field around an infinitely charged plane where the charge density is Q over A. So here's a plane. It has a total charge of Q and it has an area of A to give us a charge density Q over A. We want to ask, how do we find the electric field around there? Turns out there's a couple of ways. We can do this by doing an integration. It's certainly possible. If you're interested, your book goes through it in section 4 of chapter 23. I'm not going to do it here, and you're not going to be responsible to reproduce it on a test. And so where we'll do this mathematically is when we come to chapter 24 and we use Gauss's law. So that's where we're going to discuss the nitty-gritty of this. Again, if you're into the integration, you find it interesting, by all means follow along 23.4, but you don't have to. So let's get the idea here. What we mean by a plane is a sheet of charge where all the charges are positives. Okay? Of course, you could have a negatively charged plane as well. This plane, we're going to say, is full of positive charges. And the plane is thin. So the thickness here is infinitely small. Okay, so that's what a plane is, a two-dimensional surface. So this is our 3D view of a plane. We can also take an edge view or a side view. If we take that edge view, we could look at it as being full of our positive charges. And we can come up with the electric field. Let's get an idea of the direction of that field, and then we'll write down what the magnitude is. So if I pick some point here, I would want to add up the electric fields due to each little charge. So the electric field due to this charge would point away. The electric field due to this charge would point away. It's further away, so it's a bit smaller. The electric field due to this charge would point away. So let's put a coordinate system on here. So if this is my x-axis, this is y, then this would be z. Z is coming out of the page at us. What we see in this picture is for every charge on this side, there's one an equal distance away on this side, so the x components cancel. So Ex equals 0. Ey is not 0. And Ez, the component coming in this direction, is also 0. So the only component we have is vertically out from the plane. And the result for our electric field is that it has a magnitude of the charge density divided by 2 times the permittivity of free space. The direction of the electric field is away from the plane if eta, the charge density, is positive, or toward the plane if the charge density is negative. And epsilon naught is the permittivity of free space. That's our constant. And it has a value of 8.85 times 10 to the minus 12 coulombs over newtons times meters squared, coulombs squared. Okay, so the net electric field from this plane will point upwards. So I'm going to draw it over here on this plane. So the net field points up like this. And an interesting result is that that field is constant. So no matter how far away you are, with respect, the electric field's constant everywhere. No matter how far away you are, no matter how far up you go, that electric field is still the same. So your y component is not 0, and it is constant. That might blow your mind just a little bit. It does make sense, though. I've got a slide in the notes, which you can print, and you can do this for yourself. I had to do it for myself because I can show that it's constant using integration, no problem. But part of me was like, it doesn't really jive that it's a constant. Where does that come from? And I tried to figure that out. You can prove it mathematically, but you can also prove it using your vectors. So one of the slides in your notes has got 5 charges and a couple of points around it. What you can do is you can say that each of these charges is, say, 1 microcoulomb. Then grab a ruler and measure some distances. So you can measure the distance between a charge and a point. That's going to give you your R. You can either grab a protractor to measure your angle, or you can just measure your x distance and your r distance and use your cosine. So you can do that. What you'll see, and then draw your electric field vectors to scale. So in the lower part here, let's do those, and I'll show you why it turns out to be constant. So in my lower part, my electric field due to this charge is going to point upwards. My electric field due to this guy is going to point out. My electric field due to this guy is going to point out. My electric field due to this guy points out. And due to this guy points out. Okay, so they all point in this direction. Our result from looking at this analysis is that your electric field in the x direction is equal to 0. In the y direction, you have to add them all up. Okay, no problem. We did this on the previous slide. What about when we get further away? Because I said on the previous slide that your electric field is constant no matter how far away you are. How does that work? Okay, so for the top one, my electric field due to this charge points away, and it's not as long as this one, because if I'm only looking at this charge, this one all by itself, that's a point charge, and the electric field is kq over r squared. This one has a bigger r than this one, so the electric field due to this charge itself is smaller. That's true. So there's my electric field due to the middle charge. So my E gets smaller. Okay, that's a true fact. My electric field due to this one is also smaller than it was due to this one, but look at what you notice here. It's closer. The angle here between the vertical and this electric field is smaller than the angle here. Then likewise happens here. We're getting a bigger y component, and due to this guy, and due to this guy. So you still add up your y components here, and the overall magnitude of the electric field got smaller, but the y components increased to offset that decrease in size of magnitude. The angle changed to accommodate it. So if you want to try this out yourself, you should be able to prove that it is a constant, and this explains why. It's because the angles come in, making the y components bigger.